Good morning, super awesome algebra students. We just tested on the first half of our unit yesterday, so today we're going to be moving into unit 3B, the second half, and that starts with simplifying radicals, and we're just going to work on square roots today. So you should be on page 11 in your note packets. So let's make sure everyone's on page 11. And the I can for today is, I can simplify square root radical expressions by finding perfect square factors. And that's why we had that worksheet after your test yesterday to kind of lead us into working with factor trees and perfect squares and square roots. Okay, so let's go ahead and flip to, that page 11. First up is the product property for square roots. If I'm going to go over and define that, I'll type it. A radical expression may be written as the product of its factors under their own radical. A radical expression may be written as the product of its factors under their own radical. That's the definition. Okay, so if we take a minute to finish that definition up, I think that will make more sense if we do an algebraic model first today. So in the second box, what that's really saying is if I have the square root of a times b, I can actually break that up, and that is the same thing as the square root of a times the square root of b. Same thing. And that kind of works two ways. So, or the opposite. Square root of a times the square root of b equals the square root of a times b. Alright, if we go to the expanded form box, let's just do a little example of what I'm saying here. Let's say we have the square root of 24. Not a perfect square root, not like the ones you did on your worksheet yesterday. But we can break this up, and we can actually simplify it by breaking this up into the square root of 4 times the square root of 6. 4 and 6 are factors of 24. So if we break that up into the square root of 4 times the square root of 6, well, we know what the square root of 4 is. That is 2. And we can't simplify the square root of 6 any farther, so we have 2 square root of 6. And that is why this product property of square roots is so helpful. Okay, so that's the product property. Now we're going to zoom ahead to the second box here, and we're going to do the quotient property. I'll type that. Quotient property, the definition is a fraction under a radical can be, let me shorten this, can be written with the numerator which is the top of your fraction, and the denominator, which is the bottom of your fraction, under their own radical. Okay. So I know you can't type, so I'll give you a second here to write down what I just wrote. A fraction under a radical can be written with the numerator or the top and the denominator or the bottom under their own radical. can go ahead and pause this clip if I'm going too fast. So let's zoom ahead to the algebraic model here. Once again, this will make more sense, I think, if we have an example. So it's using a and b again. If we have this big square root, a divided by b, you can actually break that up as well and do the square root of a divided by the square root of b. And just like we did for the algebraic model of product property, this can also be written as the inverse of that. So the square root of a divided by the square root of b is the same thing as writing the square root of a divided by b. So let's do another example in expanded form. This time we'll work with the square root of 5 divided by 16. 5. So we can break that up into the square root of 5 divided by the square root of 16. We don't know what the square root of 5 is. If 5 is a prime number, we can't break the factors of 5 up into anything nice we can take the square root of. So we have to leave him alone. But we do know the square root of 16, that's 4. And so that's how you can use this quotient property to be able to simplify your square root. Okay, let's zoom ahead to page 12 in your notes. We're not going to do all of these, you have a ton of examples. But we are going to start with example 1. And I am going to have you use a factor tree, just like we did in your worksheet from yesterday. So we're actually going to start with a factor tree, since we can't actually take the square root of 12. It's not a nice perfect square. We are going to take 12 and break it up into its prime factors. So we'll start dividing it by 2. 2 times 6 is 12. Can't, 2 is prime, so we can break up 6 into 2 times 3. And now we have all the prime factors. Okay, so what we're looking for here is groups of 2. We know that two numbers multiplied by themselves are a perfect square, and a square root undoes a square. Maybe we should write a note of that. If you flip back to your summary page, you can write a little note saying, that color, saying squaring and taking the square root of a number are what we call inverse operations. And all that means is that they actually undo each other. Okay. They undo each other. So, if we have 2 times 2, we know that that's a perfect square. So I'm going to circle the 2 pairs. And whenever you have a pair, like 2 times 2, they get to come out of the radical. So we can write this as, so I'm going to kind of show you 2 different ways. We can write this as 2 squared, because that's 2 times 2, times 3. And that can be broken up using our product property for square roots as the square root of 2 squared times the square root of 3. Now we know 3 is broken up all the way, that's a prime factor of 12. But we know that the square root and the square undo each other. And the square root of 4 is 2. And we can't do anything else with the square root of 3, so we leave him alone. 2 root 3. The other way you could think about it is you have a pair of 2 here, 2 2's, so a 2 comes out. You're left with 1 3, so he's stuck under the radical. So you get your answer either way. When you're done with that, let's move on to example 2. We're going to start with the factor tree. 300. We'll divide by 2 first because it's even. Actually, forget that. We're going to divide by 3 first. 3 times 100. And I'm going to show you what I would do on this one. And that's divide 100 into 10 times 10. Because I know that 10 times 10, that's going to give me a perfect square. And I can actually stop there if I'm looking for a shortcut. So then I can come back over here and rewrite this. And the reason I stop there is because I'm already broken down into something that's a perfect square. And that's what I'm looking for. Perfect squares to come out of that square root. So we have the square root of 10 squared times your other factor, which is 3. And this is always going to get you back to the number that was under your square root in the first place. It's just another way to write it. Break that up again into the square root of 10 squared times the square root of 3. And I will even skip this step later on. The square root of 10 squared we know is just 10, and we can't do anything else with the square root of 3. So your final answer is 10 square root of 3. Okay, example 3 throws in a variable here, but we're going to skip that one, and we'll zoom on to example 4. Still dealing with a variable. So example 4, I'm going to start with my factor tree for 63. I'm going to divide 63 by 3, prime number. 3 times 21 is 63, and 21 can be divided into 3 times 7. That's as far as we can go. Do notice, though, that we have a pair of 3's. So we know that 3 is going to be able to come out of the square root. Then what you want to do with that variable, x to the 5th power, you want to break that up into perfect squares if you can. So I'm actually going to rewrite this as the square root of, and I'll start with 63. So I'll have 3 squared times 7. That gives me 63. And then I know I can pull 2x squareds out of x to the 5th power. So we have x squared times x squared. Now we know we're multiplying two numbers of the same base to add the exponents. So here you're going to have x to the 4th. Well, that's not the same as x to the 5th. And under this radical has to be the same as under this radical, just written in a different way. So we need to multiply by 1 more x, or x to the 1st power. Now we have x to the 2 plus 2 plus 1, which is x to the 5th. And now we can look for perfect squares to pull outside of our square root. Here's one. There's one. There's one. So now we can see that this is going to be, and I'm actually going to skip this step this time and see how we do with that. So a 3 comes out because we have 3 squared. An x comes out because we have x squared. Another x comes out because we have another x squared. So now we have 3 times x outside of my fraction, or excuse me, my square root. And underneath, we still have a 7 and another x. If I'm going to write this all nice and neat, I have to write this as 3 times x, which is 3x squared, times the square root of 7x. That might seem like a lot going on, but really what we're looking for with square roots is groups of 2. And I think of it as whenever I have a group of 2, like 3 times 3, or x times x, which is x squared. When I have those groups of 2, they get to get out of square root jail. So right now they're trapped in square root jail. They get to get out if they have a pair. Okay, so let's do example 5. This one's even a little bit more different than the past ones because we have a big old fraction under our square root. But if we use our quotient property, we can break this up into 2 square roots divided by each other. So we can have the square root of 25 divided by the square root of 49. And these are nice and pretty square roots. Square root of 25. You're thinking what two numbers multiplied by themselves gives us 25? Well, 5 times 5. So 5 comes out. And what number multiplied by itself gives us 49? Well, that's 7. So a 7 comes out. And that's all the farther you can go. The next one I want to try is example 6, and we are going to skip 7. So scribble up 7. Example 6, we have, we're going to break it up again. 15 x cubed divided by square root of 64. Hey, we know square root of 64. I know 8 times 8 gives me 64. So I can actually just write 8 in the denominator. And in the numerator, I want to break this up into something nice. So I'm going to do my factor tree for 15 over here. 15 is 3 times 5. Oh, darn it, they're both prime. There's no pairs, so nothing comes out of that 15. There's no pairs. So 15 is going to stay under my square root. But I know that an x cubed, I have an x squared times x. I have a pair of x's. So then one of those x's comes out of my square root. And I'll have x, that takes care of this one. Still underneath is 15 times x, and divided it by 8. And that would be your final answer. Alright, the next example we're going to do is 8. And right away, I'm going to make a little note. First, you want to reduce your fraction. If you can. So simplify that fraction. And we have 12 divided by 48. I know I can divide each of those by 12. And I'll get the square root of 1 divided by 4. And then I can break that up from there. Square root of 1 divided by the square root of 4. Well, what number multiplied by itself gives me 1? Just 1. What number multiplied by itself gives me 4? That's 2. And you end up memorizing most of these square roots. I would say up until the square root of 225. So 1 through 15. And that's your final answer. Alright, let's now look at example 9. You're kind of working backwards here. So you're saying, here is what it's simplified to. How do I get what's underneath the square root? So I realize this is kind of a lot for one day. So I'm going to go through 1 or 2 of these examples, and you can try your best on the homework on the ones like this last problem here. And if they're hard, don't worry. You can come with questions tomorrow. We'll go over this again. So you want to think, in one like this, how on earth did they get 7 out of some number that was inside the square root? And this 2, the square root of 2, that's still under the square root. So you know from the get-go that and I'm just going to blow this up and rewrite it. Underneath this square root, there's a 2 for sure, because there's 1 in your answer. And then in order to get 7 to come out, we had to have a pair of 7s. So that was like 7 times 7, or 7 squared. Well, 7 squared, we know that 7 times 7 is 49. So now I have the square root of 2 times 49. And we can actually simplify that further. 2 times 49 is 98. So we have the square root of 98. So that is actually how they got 7 root 2. They took the square root of 98 and simplified it. That's example 9. Example 10, let's skip. Do that tomorrow if you have questions on it. And we'll do 11 now. Oh boy. 11 has a lot going on. We know right away though that the square root of 2x is still under your square root. So whatever number that had a pair that came out, 2x was still left under there. So we have a 2 times x. And you know that a pair, let's first look at 6. You know the pair of 6's came out. That means that there was a 6 squared under your square root. And a pair of x squareds came out. That means that there was an x squared under your square root. So now we've looked at each number here, the 6, x squared, the 2, and the x. And we figured out what was under the square root. Now we just need to clean it up. That is a mess. So first of all, let's get all my numbers to the left. 2 times 6 squared. And we know x squared, that's a power to a power. Power to the power, you multiply your exponents. So that's times x to the 2 times 2, which is 4. And we still have this x here. Don't forget about him. 10 x. We can simplify even farther. 6 squared is 36. 2 times 36. We know when we have x to the 4th times x to the 1st, same base, so we add our powers. This is times x to the 5th. One last step. 2 times 36 is 72. Under your square root is 72x to the 5th. That 72x to the 5th is how they got 6x squared times the square root of 2x. That's all I have for you today. Thank you. Make sure you grab your worksheet and try to do as many as you possibly can and come with questions on any of them tomorrow.